Okay, we're gonna be talking about the way number 1 and number 3 still work. Typically, what you have in your system is you feeding fatty acid plus on splits, right? You get the fatty acid plus the on splits. So the whole purpose of this distillation tower is to separate fatty acid from the on splits. To achieve this separation, you need two conditions. You need full vacuum, which is provided by the ejector on top of the still, and then the temperature to boil the fatty acid. That's the way separation takes place. So you're gonna have like a steam heater that is gonna be condensing the steam on the shell side, and then on the tube side you're gonna have the fatty acid plus the on splits. So in this case, the fatty acid are the composition of the fatty acid you feed into the system, which can be coconut oil, palm oil, beef tallow, plus the triglycerides that form the on splits, right? How do you design the system? Well, you have to first estimate the dew point of the mixture. How do you estimate the dew point of the mixture? Well, you can either do the calculation by hands. In this case, you can assume that the solution behaves ideally, so you can use the Raoult's law, which requires you to use the vapor pressure of the pure compounds. If you're gonna go, more fanciful calculation, you can use your processing libraries such as ChemCat, Aspen HYSYS, ProMax, Pro2, or any other one that it's available at the moment of performing the calculations. So it's for you. It is key to know the composition. So you're gonna have to know the composition of the fatty acid, all right? It's typically C8s, C10s, C12, C14s, C16s, and C18s, depending on the oil. If you got soybean oil, it's gonna be one composition. If you got coconut oil, it's gonna be over the one. If you got palm oil, it's gonna be a different composition. So two things you need to estimate. Number one, bubble point, and then dew point. Right? So how do you know the pressure? Well, the pressure is the best vacuum you can pull in the still. In this case, it's gonna be 15 millimeters of mercury. Why we know that we got 15 millimeters? Because we know that at the top of the still, we usually carry 5 millimeters, between 4, 5, and 6. Why you have a higher pressure at the bottom of the tower? Well, because there's a device that prevents the entrains, the gas, the vapors coming out of the pot, and separates the mist from the vapor flow. So you got something that they call the mister pad in the one hand, right? And in the other hand, you got the chevron separators. So the whole purpose of the mister pad and the chevron separators is to de-entrain the vapors coming out of the pot and going to the vacuum system and going to the condenser, so you can create the fatty acid in the liquid phase. So you got 5 here. You can assume that the pressure drop across the two separators is 10. That implies that you're gonna have 15 millimeters of mercury absolute at the bottom of your still, right? With this in mind, and the composition of your fatty acid, you're gonna be able to estimate your dew point. Why you need to estimate the dew point and not and to design your heat exchanger? Well, because if you feed the fatty acid at its bubble point, you won't be able just to achieve full separation of the fatty acid from the on splits. You need to calculate the dew point. That's gonna guarantee you that you're gonna be flushing 100% of the fatty acids, and you won't be leaving any fatty acid on the unsplit stream, which is the bottom loop that recirculates throughout the system. Once you select the temperature, once you calculate the dew point temperature, you're gonna be able to calculate how much steam you're gonna need to get there, right? So you know this temperature. Assume that you are separating coconut oil fatty acids. Well, we kind of know that temperature of boiling of bubble point of fatty acids is in the 330s, and the dew point is going to be in the high 280s. Typically, we've been running between 388 and 392 degrees Fahrenheit. So we kind of know the temperature here. So 388, right, and 392 Fahrenheit. That's going to be the bubble point of the dew point of the mixture at these conditions, right? There's one key ingredient that we have to be aware of, which is providing enough energy in the form of enthalpy of vaporization to the mixture in order to achieve 100% separation of the fatty acids from the bottom stills loop, which is 100% on splits. So for you to solve this equation, you have to estimate the flow rate. How much flow rate of bottoms you require to circulate throughout the system to provide enough heat to the fatty acids to be flush 100%. Well, we know that the fatty acids have enough sensible heat, which is going to be equal to M on split, right, times Cp of the on splits times delta T, right, is going to be equal to what? To the sensible heat of the fatty acid, so it's going to be M fatty acid times Cp of the fatty acid times delta T, plus what? Plus the latent heat of vaporization of those fatty acids. That's the way to solve this issue, to solve this problem. You need to calculate how much on splits are necessary to provide enough heat to vaporize. And that, guys, this delta T is decided by the designer of the steel, which is typically 20 degrees Fahrenheit. That's the reason, guys, you see there's always a 20 degrees difference between the fit to the steel and the temperature coming out of the steel, from the bottom of the steel. So typically you're gonna have 20 degrees of the differential temperature. So in this case, your temperature is gonna be what? In the 368 range, right, to the 372 degree Fahrenheit range. So this is your only unknown on this energy balance, right? This is your energy balance equation, right? You need to calculate this one, the Cp of the triglyceride. Delta T by design is going to be 20, right? Flow of fatty acid, it's given because that's the amount of fatty acid you feed in to the system, right? The Cp of the fatty acid, you know that one, you can estimate that one. Delta T is going to be what? The temperature at which you are feeding the system, which is room temperature, you know, coming from the storage tank, which is 120 degrees Fahrenheit. And you have to get there to the dew point of the mixture, which is going to be 388, 392. So you know this delta T as well, right? And then you're going to have to include the latent heat of vaporization of the mixture. So you can calculate the amount of on splits that are going to be circulating. With this in mind, that's going to be good for what? for estimating the total flow of on splits that are going to be circulating throughout the system. It's going to be enough to help you size the pump, and it's going to be helpful for you to size the heat exchanger, your heater. That's the way you solve a distillation column to separate fatty acids from on splits. That's the way you get it done. Thank you very much, and I'll see you in a different time.